Hi, my name is Bruno, and in this video I'll introduce you to the main ideas and results of our recent work on the spiked matrix model with generative priors. We all know that the structure of data plays a very important role in machine learning tasks, and knowing how to capitalize it can make a major difference in training a model. In recent years, generative models for data, such as variational autoencoders and generative adversarial networks, gain in popularity. These generative models exploit the expressivity of neural networks to create low-dimensional latent representations of datasets. On general grounds, we would like to understand how can we use these generative networks to improve signal reconstruction. For example, say that we want to denoise a corrupted image of a face. If I train a GAN on a given dataset of photos, can I use the GAN as a prior to improve reconstruction? In our work, we study these questions on an analytically tractable setting. Our playground to explore this question will be rank 1 matrix factorization. In this problem, we are given a matrix Y generated from adding noise to a rank 1 matrix, and the aim is to reconstruct the exact realization of V star, knowing this context as the spike. This model is widely studied as a proxy for principal component analysis, and indeed PCA is an optimal algorithm when the spike is unstructured. But what happens when V has a lower dimensional structure? A popular way to model this is to take the spike to be sparse. In this case, it is not surprising that PCA is no longer optimal since it doesn't use any information about the sparsity. Many algorithms, known under the umbrella of sparse PCA, are able to improve over vanilla PCA. However, quite strikingly, no known algorithm is able to reach the statistically optimal noise threshold in this case. Instead, what if we take the low-dimensional structure to be encoded by a deep generative network? Can we do better? Spoiler, our work showed that yes. We derive and rigorously prove a formula describing the performance of the base optimal estimator for any distribution for the spike. In particular, when this prior is taken from the ensemble of random generative networks with IID weights, our formula is valid for any distribution of the latent variable and for any choice of activation functions. We also derive an approximate message passing algorithm to estimate the spike from Y. We show that the performance of our AMP algorithm can be tracked down exactly in the high dimensional limit. In particular, for the most common architectures with activation functions to be linear, ReLU or sine, the AMP performance coincides with the optimal performance of the Bayesian estimator previously discussed. In other words, different from sparse PCA, there is no algorithmic to statistical gap for studied architectures. We also propose a simple and easy to implement spectral method derived from our AMP algorithm, and show that it starts to correlate with the spike at the statistically optimal threshold. In particular, it always beats PCA in performance. Curiously, our spectral method depends on the structure of the spike only through its covariance. This suggests we can apply it to arbitrary structured data by using the empirical covariance instead. We probe this experimentally by choosing a spike from a real dataset, fashion and mist. Surprisingly, our spectral method beats PCA even though the spike is not drawn from a generative model. Unfortunately, time is short, and this video is just a taster of the main ideas and results of our work. If you got curious and wants to know more, please do pop by our poster on Friday, or send us an email to arrange a discussion. See you in Euribs.